I feel like the logic behind these optimization problems can be initially not very intuitive, but the each step actually does make a lot of sense once you understand it. And also by understanding it, you have a deeper understanding of how to solve the problems and you'll be much better equipped to solve them. So this question, and excuse the kind of low quality text up here, but this question tells us that a manufacturer wants to design an open box having a square base and a surface area of 108 square inches. And it asks, what dimensions will produce a box with maximum volume? So the first step in these problems is to figure out what you have to do and to set up an equation for that, for maximizing or minimizing that parameter. So in this case, we're maximizing the volume, right? So we're maximizing, we'll call it V. And the equation for V in this case, if we want to mark up this picture, so we know it's a square base, so x by x, and we'll call this the height y. So the equation for volume is base times height, so x squared y. Now we have to simplify our equation here to only have one variable. So let's get rid of y. So we can use our given surface area of 108 square inches to find what y equals in relation to x. So it's going to equal 108 square inches. And this is going to be x squared, right? X times x. And then we're going to add xy. And then this other face is also xy. This face back here is xy. And this face in the front is also xy. So the surface area is x squared plus 4xy. And now we just simplify to find what y equals. So we go 108 minus x squared equals 4xy. Then we divide by 4x. So we go y equals 108 minus x squared over 4x. So now this is the first step that you could overlook or not really think about it in terms of why it makes sense and what the logic is behind it. So by having this equation and then using this other equation of the surface area, we're applying a restriction to our original equation. So by using this given surface area and then plugging y in terms of x using the given surface area and back into our main volume equation, we're applying the restriction of a surface area of 108 inches into our equation. And you may not even think about how you're doing that, but that is really what's happening, is you're applying a restriction to this volume equation so that it applies to this specific problem where we have an open box with a square base and a surface area of 108 inches. Now the final step is finding the derivative of this new equation, or v prime of x, and then you set it equal to 0. And I'm not going to go through that whole process because it's not really necessary for explaining the logic. But what you're really doing by finding the derivative of this equation and setting it equal to 0 is you're taking this function that shows the volume, so let's say v of x, right? You're taking this function that shows the volume for different inputs, so let's just pretend it, I don't know, looks something like this. And the derivative equals 0, right? The tangent line equals 0. It's at a maxima. Shouldn't say maximum, could also be a minimum, but in this case we're looking for a maximum. So we're taking our volume graph, right, this function, and we're finding where the derivative equals 0. And when the derivative equals 0, the volume, right, because we're trying to find the maximum volume, the volume is at a maximum, right? The volume is at the highest that it can be. So that's why you set the derivative equal to 0 when you're trying to find, what box will have the maximum volume or what box will have the minimum surface area. You're just finding local extrema on this graph of V. And these points represent the volume, right? The output, this is x, obviously, and the output represents the volume of the box, right? So this axis represents the volume of the box. So we want to find where it's at a maximum so that we can have the maximum volume.